On March 12, 1998, American astronomers shocked the world by reporting that a large asteroid could potentially hit the Earth within 30 years. Could humanity survive the impact of such an asteroid? At this time, there is no definitive means to protect or defend ourselves from the inevitable global devastation this event would ultimately cause. This program profiles some of the most spectacular comet and asteroid impacts on the Earth, as well as the current and future dangers of such impacts to the survival of the human race. Also portrayed are the current measures that space programs have already set up to observe, detect, locate, and track these celestial objects near the Earth that may someday pose a distinct threat. Future plans include the sending of robotic spacecraft and even human exploration missions to any threatening asteroids or comets in order to deflect or destroy them.
Important as the continuing reign of comets and asteroids is on the Earth today, it is nothing compared to the conditions at the birth of our planet 4.5 billion years ago. Then the Earth itself formed from an accumulation of cometary and asteroidal debris, and some of those impactors were extremely large.
If you look at the Moon, it's heavily cratered. If you look at Mars, heavily cratered. Mercury's heavily cratered. The Earth was also heavily cratered. It's just that here on Earth, the effect of all the erosional processes and the tectonic processes which create mountains and earthquakes have erased the record. But in fact, the Earth would have looked just like those other bodies had it not been for the weathering and the tectonic processes, the geophysical processes.
Very early in the Earth's history, we are fairly sure it was struck by an object about the size of the planet Mars, which ruptured the planet, ejected a great deal of material into orbit around the Earth, and it is that ejected material from a giant impact that ultimately formed the Moon.
The Moon, of course, is pockmarked by craters upon craters. Most of these, however, were created back in the early days of the formation of the solar system, and when there was a lot more material hitting both the Earth and the Moon. There is not much of that material left, so the Moon does not have as many recent craters, but certainly there are recent craters on both the Earth and the Moon.
In cultures as diverse as the ancient Greek, the ancient Mayan, the ancient Chinese, those cultures didn't interact at all, but they all feared comets. And into the Middle Ages, when the church was well established, they utilized this fear, suggesting that comets were warning signs shot at a sinful Earth from the right hand of an avenging God. And then in the 17th century, when Halley and Newton showed that comets are not warning signs from an angry God, but in fact celestial objects moving around the sun just like the planets, the fear of comets was sort of transferred from a sign of an impending disaster to the actual agents of disaster.
The largest well-documented impact was 65 million years ago. We don't know if it was a comet or an asteroid, but we do know that it struck the Earth in the Yucatan region of Mexico, producing a crater about 150 miles across, and that it created such a profound environmental catastrophe that most life on Earth came to an end. The majority of the species went extinct, including the dinosaurs.
There's a local crater here in the United States, in Arizona, that was created by something a little smaller, we think, about 150 feet in diameter, 50 meters. That is the meteor crater near Flagstaff, Arizona. And it did create a crater because it was, the asteroid was iron, very solid, very massive. It made it all the way through the atmosphere and created a crater that is almost a mile in diameter, 1.2 kilometers, I think, and about 200 feet deep.
There have been several instances of comets and asteroids smacking the Earth. The most recent, perhaps, is the so-called Tunguska event in Russian Siberia, where in 1908, an object probably the size of several houses smacked into the Earth's atmosphere and caused an explosion that knocked down trees for 30 miles in either direction. And this was an object that was only about 60 meters in size, just over the half the size of a football field. And it didn't even hit the Earth because it broke up in the Earth's atmosphere.
There are countless craters all over the Earth. It's really surprising. We probably know of only a small, tiny fraction of all the craters that have been created by impacts. Most of them have been eroded away and are very difficult to find. We know of something like about 130 to 150 craters currently on the Earth.
The Earth orbits the Sun in a sort of cosmic shooting gallery with comets and asteroids coming by all the time. At any particular moment, there's likely to be one or two between us and the Moon that are 30 or 40 feet in diameter or larger. We don't usually distinguish between comets and asteroids because once it hits, it really doesn't matter what it was. Asteroids are made of rocky material, comets are made of icy material, but if you're hit by one, it really doesn't matter any more than you would care if you were shot, whether the bullet that shot you was made of lead or steel.
There are millions of asteroids out there. Most of them are small, and it's the asteroids that are 1 kilometer, half a mile or so, and larger that we really want to make sure we detect and catalog. And we know only about 10% of those. So the current search efforts are focusing on those rather larger asteroids. But there are many more smaller ones, and in fact, every day little asteroids pass the Earth. We simply don't see them.
We know so little about these objects that we don't even know whether they're all traveling in the same direction or what their orbits are. We don't know if they have very highly inclined orbits relative to the plane where all the planets travel. We don't know hardly anything about these asteroids that come in and that are very difficult to detect. These are basic questions. Where are they going and where are they coming from? We don't know the answer.
There are about 2,000, we believe there are about 2,000 objects which are potentially hazardous to the Earth. Of those, we know about 10%. And we're learning about 1% more every year at the current program level. If NASA were to increase the program level, we could probably complete the inventory in about 10 years.
It's just that we simply have only looked at and found 10% of the, I hate to say this, of the estimated population of near-Earth asteroids. We estimate that there's between 1,000 and 2,000, very widespread. The point is we now know of over 100 asteroids which we call potentially hazardous objects. And by definition that means that these objects can come within 5 million miles of the Earth.
The velocity of these comets and asteroids depends on their distance from the Sun. The fastest objects in the solar system are probably comets. They come in from deep outside the solar system, and they arrive at the Earth's orbit with velocities that can reach 73 kilometers per second. That's about 73 times faster than the fastest high-speed bullet.
In contrast to the Apollo missions, where it took approximately 2.5 or 3 days to go from the Moon to the Earth, a typical comet would take something like an hour and a half to 3 hours to travel the same distance.
Something that you think is coming towards you, particularly something that can get from the Moon's orbit to the Earth's surface in under 3 hours, 5 million miles is not all that far.
Fortunately, we on Earth have an atmosphere that protects us from small impacts, so we don't have the sort of daily rain of dust-sized particles that the astronauts experienced on the Moon. However, the atmosphere is of no use in protecting us. It provides us no shield from the big impacts, those that are really hazardous. A comet or asteroid a mile across punches through the Earth's atmosphere just like a fist through a cobweb. It might as well not be there.
If an object as large as 10 miles across hits the Earth, then it causes enough havoc to wipe out a good fraction of the life forms on the planet. But these events are very rare. These are maybe several tens of millions of years apart on average. They're extremely rare. Much more common events are impacts by much smaller bodies, say kilometer-sized objects. There are probably 1 to 2,000 of these that can conceivably impact the Earth, and if one of them hits, it will be much less catastrophic than the kind of an impact that can wipe out lots of life forms, but nonetheless, it will be terrible and probably will end civilization.
The reason we are concerned about impacts of objects even as small as a mile or two across is that it turns out that the Earth's ecological system, its environment, is very fragile. These are not impacts that make any difference to the planet as a whole. They don't change our orbit, they don't change our spin, they don't change the axis of rotation. They're nothing to the planet as a whole. But the impacts are able to produce environmental catastrophe. It's really a measure of just how sensitive the balance is that allows life to flourish on Earth.
We should have, in the case of a comet, perhaps a year or two to react. In the case of an asteroid, we should literally have decades. So with an asteroid, we should have plenty of time. In fact, the technology we have today is probably not the technology that we will actually use, because the event is likely to be some time off when our technology will be much more advanced than it is today.
I've done research into this area. I took the comet Hyakutake, in fact, as an example. That was a comet that passed by the Earth in 1996. And it passed fairly close to the Earth, astronomically speaking. The comet was only discovered 3 months before it passed by. The answer to the question really is that we couldn't predict that it would hit the Earth until about a month before the event. And that is probably typical. Most comets are not discovered until about 3 months before they pass by the Sun. So we're talking about months here. Many of these objects are whizzing by us daily, and we won't know when the next one happens, quite likely, unless we have a good campaign of searching for all of the objects and cataloging them. We may miss them entirely, and the next impact could happen entirely tomorrow.
In general, the astronomers look at maybe 10 or 15% of the sky. So most things coming in would be missed. If you ask the question at today's level of effort, what warning we would be likely to have of the next impact, the most likely warning is 0. The first you would know about it is when you felt the ground shake and saw the plume of hot rock vapor coming up over the horizon.
Whenever somebody at a high level within the military would raise this planetary defense issue, should the military be worried about objects from outer space smacking into the Earth, their colleagues would always start snickering and giggling and say, oh no, here we go, it's a Chicken Little defense. We don't have to worry about this. And so that happened a lot 10 years ago, and it's happening much less now, probably because of Comet Shoemaker-Levy 9 smacking so dramatically into Jupiter in July of 1994. If it can happen to Jupiter, it certainly can happen to the Earth.
The impact of Shoemaker-Levy on Jupiter several years ago was a very important experimental laboratory for us, because These are very rare events. Impacts with Earth of this magnitude are very rare, fortunately. So here was an opportunity to observe the impact of many fragments of a comet, actually, on another giant planet. The total amount of energy deposited by these fragments of Shoemaker-Levy were millions of megatons. So this was much more than just a single hydrogen bomb. These are massive eruptive energy deposits, creating these huge plumes.
We could see the 20-odd impact sites as little clouds of dust. Essentially, the comet was vaporized when it hit the atmosphere. And these dark clouds on Jupiter's atmosphere and the rings around them were larger than the Earth in size.
Should a comet or a large asteroid strike the Earth, the devastation would be immediate and sustained. There would be long periods of very dark weather. The sunlight would be shut down.
The impact will produce devastation immediately where it occurs, but it can throw up a lot of material that gets vaporized, rocks and whatnot are thrown up, much of it out of the atmosphere. And a lot of this stuff will then spread out but come back down in a much larger area. When it comes down, it will produce firestorms because the material is very hot. It'll produce smaller impacts, but impacts as well. It'll throw up, a lot of the dust will remain in the atmosphere.
Some of the effects that we would expect would be that the dust generated from this enormous explosion would float up into the Earth's atmosphere, surround the Earth, shut down the sunlight, so things would get much colder than they are now. The plants, the food chain would be disrupted because the plants no longer would have enough sunlight. It would be a pretty nasty situation.
In terms of the human species as a whole, in the immediate after effects of the impact, if it hits in water, it's a lot worse because the human population tends to be around the coastlines. And anything that big hitting the ocean is going to create a tidal wave that's going to make the Manhattan skyline puny. You're literally going to see saltwater and tidal waves coming in hundreds and hundreds and hundreds of miles on the coastlines. If you're in that area, one hopes one has that you've gotten your affairs in order and have made your peace, because there's no chance.
Impacts represent a natural hazard. In some ways, they're just like hurricanes and earthquakes and volcanic eruptions. They're part of nature. They've been with us all along, but they are different in two important respects. First, only cosmic impacts are large enough to threaten the survival of humanity or to possibly create mass extinctions. No imaginable level of earthquakes or volcanoes or any other kind of natural hazard has the potential for killing billions of people at one time. The second distinction is that they are the only natural hazard that we have the potential of doing something about. There's no one that can imagine a way that you could stop an earthquake from happening or tame a hurricane or plug up a volcano. But if we had adequate warning of a comet or an asteroid headed toward the Earth, then we do have the technology to deflect it, to change its orbit so it would miss.
The first thing we do is to identify the entire population of potential threatening objects. There are search systems in place now. The NEAT project between JPL and the Air Force is in place, and they're discovering near-Earth objects. And there's a program at the Lowell Observatory that's coming online. So the first order of business is to find out the entire population of potential Earth-threatening objects, the large ones that are larger than, say, a mile or so in diameter. We only know 15% of that population now.
NEAT is an observing program, an electronic detection system that allows us to search the skies as rapidly as we can with charge-coupled devices on a 1-meter telescope. Each night from the Jet Propulsion Laboratory, we prepare an observing list of those fields in the sky we want to cover for that night of 10+ hours.
The telescope is located at the Air Force Observatory in Haleakala, Hawaii, which is a mountain in Maui. And every run when the moon becomes new, we're able to search the skies at this darkest time. And somebody there mounts the instrument on the telescope, connects the electronic camera to the back of the telescope, and then the computer takes over from then on. It automatically controls the telescope and controls this electronic camera and finds these moving stars in the images recorded by the camera. This is automated asteroid detection.
Initially, when an object is discovered, it's just a speck on a picture, really, electronic picture nowadays. And typically, it might have a little coma around it if it's a comet. You don't have any idea how far away it is. You have to take a series of images over many days in order to get any idea of where the object is going. But using mathematics and the well-known Newton's equations of motion, you can determine what the orbit is, very crudely, after, say, a week of observing an object.
The first step in terms of addressing any potential impact is to very accurately determine what its trajectory is, so we can be sure of exactly the trajectory it's on and when and where it might impact, and how long we have. That is the very first step, and certainly for that step, JPL would be heavily involved because of the capability we have to do these inventories, which we're doing today.
It's just that we have each night 500 or 600 new asteroids. We cannot start checking out orbits on all of these. Of course, we occasionally do get a little impatient, and we will run orbits of those we're most eager about, finding out what the preliminary orbit is. We have a good sense of, based upon its motion and where it's located in the sky, as to whether it's going to be a near approacher.
Now, it's important, if it's a dangerous object, something that appears to be coming close, it's important to keep tracking that object, because the longer you track it, the more observations you take of this, the more pictures you take over an extended time, the better you know its orbit. And we really need to know a precise orbit in order to predict whether it will hit the Earth, and if it will, when it will hit and where it will hit, and that sort of thing.
Suppose we discovered an asteroid that looked like it might be on a collision course with Earth during the next 10 or 20 or 30 years. The very first thing we would do would be to try to do radar observations as well as more extended optical observations to shrink the uncertainties in the orbit and find out if it really was going to hit. This would be possible over a period of years. It would not be possible over a period of months, so we would have to have at least a few decades, at least a decade or two of warning to do this really right. But then suppose we got to the point where we knew an asteroid was going to hit the Earth. And then we would decide what strategy we're going to use to protect ourselves.
Comets, long-period comets in particular, provide a greater problem. First of all, because they are coming at us from the depths of space where we can't really see them until they approach. Secondly, they're dark objects to begin with. They're traveling very fast when they pass the Earth, 2 to 3 times faster than an asteroid would pass the Earth. And finally, they have this outgassing characteristic where the frozen gases inside the object spew out as if from geysers, and that tends to move the trajectory around. That will actually push them and change their course slightly, but enough that over time it may create a hit or a miss. So they are very difficult, and we cannot be sure until a month or two before it passes the Earth, whether or not it would hit the Earth for a comet.
Once you have identified a potentially hostile comet or asteroid, then with decades of warning, you would have the opportunity to investigate it. You'd send a spacecraft like the current NASA NEAR mission, which is going to a near-Earth asteroid. You would measure its size, its rotation, its shape, its composition, whether it was one solid rock or a rubble pile. Try to find out what it was like.
We can't just send up a rocket and set off a bomb because, for example, we don't know if the object is two objects in orbit around a common center of mass. It might be a binary asteroid. Even if it's a single object, we don't know its interior properties, and the response of the object to a bomb is going to depend in detail on its interior properties, whether it's fractured down the middle, whether it is two objects in contact. We really could be making a huge mistake if we just send a bomb up there to deflect it without exploring it in great detail. So what we're going to have to do is probably send a whole fleet of robots to inspect the object.
If you do decide that you want to move a comet or an asteroid, that you want to move it aside so it's not going to the Earth, the only way we have to do it is with nukes. You're not going to do it with lasers. You're not going to do it with particle beams. You're not going to go out there and attach a little rocket engine. It's an enormous amount of mass for anything that we're actually going to be worried about, and you have to move it. The only way to get that kind of concentrated energy, especially in the kind of missile or spacecraft that we can launch with current technology, the only way to do that is with nukes, and big ones, and lots of them.
One obviously must be careful in trying to apply any sort of defensive system, and in particular in setting off a nuclear bomb as a way to deflect the orbit. If you hit it with a nuclear bomb, if you use too big a bomb, there's a danger that you would break the object apart and increase your danger, actually, because now the Earth might be hit by several objects instead of one, sort of changing a cannonball into a cluster bomb.
We would probably have to send some sort of a nuclear weapon into space, set it off one asteroid radius off the surface, and ablate the material on the front side of that asteroid so it actually acts as a rocket-like engine and pushes the asteroid aside just a bit so that in 20 years, when it's predicted to hit the Earth, it doesn't hit the Earth because we've modified its trajectory just enough so it misses the Earth in 20 years' time.
If you use small explosives, if you set them off not on the surface but in space nearby the object, you can apply very gentle pushes. At least we think so. We've never done this. This is just theory. And so I'm telling you what I think our technology could do, but I don't pretend that this is a mature technology and that we would be ready tomorrow to try to defend ourselves if an incoming object were discovered.
There are, of course, treaties that forbid nuclear weapons in space. And so this would have to be an international process whereby these weapons are delivered to the asteroid and this asteroid is slowed down. But after all, the threat is an international threat. It isn't going to hit New York or Los Angeles or Moscow. It's going to hit everywhere.
We might even have to send people there very quickly to set up seismometers on the surface, to determine the gravity field, to try to psych out what the interior is like before we ignite a nuclear bomb. Now, there's a nightmare scenario here because all asteroids have suffered collisions and they're all fractured, and we know, for example, that some of these objects are two lobes touching each other. In that kind of a situation, if we set off a bomb near one lobe, we'll destroy it completely, but we know that we would not do anything to the other lobe. We wouldn't even change its orbit. So we could go to all this work, we could set off a powerful nuclear weapon, and it would not save us.
Except for the minor problem of needing to bring them back, humans would be ideal for a situation like this, and from the standpoint of being more dexterous, more intelligent, more able to make decisions on the fly and more able to generally react to the situation that they find than a robotic device would be. But when it comes to the other side of the equation, which is that supporting humans for a long space flight is a big problem. And of course, in the situation where you're trying to save the Earth, you would take a lot of chances, you would cut a lot of corners. But probably the biggest single thing that would make humans not an attractive option for this is the need to try and bring them back.
And so we're sitting here, we don't know anything at all about the object, and we have to make decisions about what launch vehicle to use, what kind of a nuclear device to use, what its total energy yield should be, what the timing should be, how this big project is going to be orchestrated, and so forth. And yet we don't know enough about the enemy. Moreover, we can't learn enough about the enemy without sending a whole bunch of spacecraft to it. We might not be able to learn enough about the enemy without sending human beings to the object.
Fortunately, I think if we were to have this kind of event, an awful lot of the training that we conventionally do for the things that we do now, which includes rendezvous, proximity operations, spacewalks, working with tools outside, handling of large objects, all that would be applicable to the kind of mission that you would put together if you decided that you were going to try and stop a comet by going and landing on it or docking with it really and blowing it up, or trying to deflect it by placing charges. The stuff we're doing now for space station would be as applicable as anything for that.
It's going to be much more like some of the early lunar landings where they had to take over computer control and redirect the lander away from those boulders into something that was much more smooth. But it's going to be that to a much greater degree.
We're mostly not quite that suicidal, so I think that you'd find that most people would want to have some chance of getting back. But again, the idea is that the world is in danger, and so these people are obviously prepared to take a lot of risk. And I think it's fair to say that most of the people that I know who are in the astronaut corps have something of that in their characters, or they wouldn't have volunteered for what is inherently something of a risky business to start with. So it's a little riskier than what we do on an everyday basis, but it's the same kind of folks.
Recognition of an impact hazard is a real natural hazard and something we should perhaps worry about. It's quite new. It's only in the last few years. So far, the U.S. Congress has commented on it. The Parliament of the European Union has. There have been a number of meetings, but no one has clearly stepped up and taken a leadership role and said we should spend the money and we should carry out the survey. I hope that there will be increasing interest on an international level in doing that, but we aren't quite there yet.
Most people do not see this, do not understand this threat. And one can understand that response because the threat is very unlike anything else in human experience. It's really very new idea, and it takes a while to get used to it.
I think the scientific community has a job on its hands to educate the public as to this threat of comets and asteroids. I mean, every day you have car accidents. People can identify with those. Every few months we have airplane accidents. People can identify with those. And so these are perceived as real threats. But when you talk to the public and say there's perhaps going to be a large impact of a comet or an asteroid, most people will say, well, why don't we wait 250,000 years and then worry about it? But what the education process we have to go through is that this could happen tomorrow morning, or it could happen 3 million years from now. And this is the education process that we have to go through to educate the public and the Congress to this type of threat. And so the proper resources can be put forward, and they're very modest levels of resources for finding the entire population of Earth-threatening objects and keeping an eye on them.
There are a few astronomers who make a profession of scanning the sky with advanced telescopes looking for potentially threatening comets and asteroids. It's very few. In fact, the total number of people involved in searching the sky is less than the staff of one McDonald's restaurant. That is the level at which we, the people of planet Earth, have taken this issue and are trying to solve it. So the proposal that has been developed first by the NASA study and then by international bodies is to carry out what we call a Space Guard survey, a simple telescopic survey to look for potentially threatening objects. It would cost about $10 million a year for 10 years. And at the end of 10 years, we'd be able to answer, at least at the 90% level, the question, is there something coming our way that poses a threat to the planet, or is there not?
One normally has homeowners insurance to pay for protection against very unlikely but potentially catastrophic events. The asteroid-comet collision hazard is similar. The potential catastrophe from one of these impacts is very large, but fortunately, the insurance that we need to protect against most of that risk is very cheap. It's a tiny fraction. It's less than 1/1000th of the budget of NASA, for example. It's a tiny amount of money with enormous return on the investment.
I think it's imperative that the public and our government understand the serious nature of this possible threat. The only way we can evaluate how serious this might be is that we have to complete the survey of the skies, a comprehensive sky survey, probably for at least 10 years with multiple telescopes in order to evaluate whether we have some concern based upon our near-Earth objects. And I think this is probably the most important aspect of this work, is to bring home the message that we simply do not have a good grasp of our nearest neighbors in space. We want to find them before they find us.
The cost of the space station ultimately will be at the $10 billion level. The cost of a human mission to Mars ultimately will be at the $100 billion level. And all these costs are huge compared to the several million-dollar price tag on a really high-powered optical system to discover the possibly threatening Earth-crossing asteroids. We have tried to interest governments around the world in providing the minimal support that would be needed to do this job right, and we have failed. I think the decision makers either do not really understand the simple facts, or they simply don't care. Or, in the democracies, I think the governments believe that the people don't care.
We spend so much more on other rather trivial things that this is, as I say, a very inexpensive way to allow the scientists to identify whether there's a menace out there, and if there is, have enough time to make or plan diversionary methods so this object will not strike the Earth and we will suffer the consequences as the dinosaurs did 65 million years ago.
I think most people who really understand the science of near-Earth objects, all the characteristics of the hazard, all the potential of these objects, are at once very excited by it and befuddled by the reluctance of the governments of the technologically adept countries of the world with big space programs to fund this work. It's a mystery.
To put it in perspective, I mean, these impacts, deep impacts, like in the movie, of very large objects, are very rare events. They don't happen that often. It's what we're buying if we go out and look for things is certainly some science, but we're also buying insurance. And as insurance, what is it worth to prevent the 1 in a million chance that all life as we know it will end?
Comets and asteroids are not only interesting because they pose a potential threat to the Earth, they're scientifically important because they represent the leftover bits and pieces from the early solar system formation process. So if we wish to study our origins, from what chemical mix did the Earth ultimately evolve, then studying comets and asteroids are the way to do that because they're the most primitive, least change objects in the solar system.
We've flown by 2 asteroids already. Galileo did that on its way to Jupiter. Galileo arrived at Jupiter in December of 1995, but on its way there it flew by 2 asteroids and gave us our first close-up view of these bodies in outer space. And we even discovered that one of the asteroids had its own small moon.
The asteroids offer resources for titanium, for iron. So if we want to build structures in space, we don't build them on the Earth and then take them to space. We build them in space, mining the asteroids. It's been estimated that if you take all the resources of the asteroids between Mars and Jupiter, and in terms of today's dollars, the titanium, the iron, the cobalt that is available, it works out to something like $20 billion for every man, woman, and child on the Earth's surface. It's extraordinary.
We're starting to appreciate all the reasons why the Earth-crossing asteroids are important. Because of the threat that they pose, also because of the promise that they hold. I think that we're living in that era of discovery. And I also think that the singular event that would mark our place in history would be a mission of people to land on a near-Earth asteroid. And this could be done within the next 10 years. It would be dramatically cheaper than a mission to Mars, dramatically easier than a mission to Mars, and it would be the first step off of our planet into the solar system to these worlds that really are just huge numbers of space stations waiting to be inhabited.
If mankind is ever to move off the Earth's surface and start colonizing space, then we're going to need metals, we're going to need rocket fuel, and rocket fuel is nothing but hydrogen and oxygen as an oxidizer, and these are found in abundance in water, and water, ice, is found in abundance in comets.
We're going to be launching another mission called Stardust in January of '99. That mission is designed to capture some dust of a comet as it flies through the comet tail, collect that dust and bring it back to Earth in January '06 so that we can analyze what this black organic-like material is that coats the comets in the solar system.
And so in the next century, I'm firmly convinced that the asteroids and the comets will be utilized as resources as mankind steps off the Earth's surface and into the great interplanetary ocean.
the best way to make sure the human race isn't wiped out by a large object hitting the Earth is to make sure we aren't all here. I believe that the best hope for mankind is to move ourselves, obviously not too many of us at a time can go to start with, but off the Earth and get going on out into the solar system and on eventually to the stars. It's interesting to me that we have a society that can absorb a limitless amount of Star Trek and all the other futuristic stuff that we see in movies and television, and yet we don't spend very much of our real today money taking even the baby steps that it takes to make true interplanetary exploration possible. And believe me, in the great scheme of things, we're far more likely to preserve the human race by making sure we aren't all here when the comet hits than we are by trying to do something to stop it.
Every part of our planet is equally subject to impacts. There's no place that is more likely to be hit or less likely to be hit. And when it comes to the big ones, the ones bigger than a mile across, it really doesn't matter where they hit. If the Earth were hit by an object a few miles across, it would ruin your whole day or your whole year, no matter where it hit. And that's one reason that there has been so much international interest. It's one of the things that threatens the whole planet equally, and it seems reasonable that any solution that society comes up to ought to be an international solution. Everyone's equally at risk, and every country can contribute to solving the problem.
If the human species is to have any chances of survival in the future, the first step is to increase our awareness of the global threat of a comet or asteroid impact, then to be able to set up the necessary defensive procedures in order to avert such a disaster. At present, we cannot even locate all of the potentially dangerous objects in space. The ability to defend ourselves from the civilization-ending danger does not yet exist. It is only in its infancy of planning and development. The dinosaurs could only feel the ground shake and watch the plume of impact dust coming up over the horizon, just before the resulting global catastrophe caused them to freeze and starve. If we cannot learn from the past, then humanity as a whole is doomed to experience the same exact fate as the dinosaurs. That could come as early as tomorrow morning.